Hello everyone, my name is Rafał Bielas. I'm PhD student at Adam Mickiewicz University from Poznań, from Poland. And today I'd like to talk about our work on ultrasound and Pickering emulsions. I'd like to express my gratitude to European Acoustics Association for conference grant. At first, let us assume pure droplets without any coating dispersed in liquid. We call this system emulsion. And the system, as we know, is inherently unstable. So we want to make the system more stable. To do this, we use commonly surface-active agents. They lower surface tension and also, as a result, lower total energy of the system. However, there are some limitations of using surfactants to stabilize emulsions. First thing is quite poor stability of the system. The second is problem with hazards for environment and also difficulties in recycling of these chemicals. Also, there are some problems with tissue irritation, like our skin and our eye can be irritated by surfactants in emulsion. It limits very much the using of surfactants in biomedical applications. What can we do to solve these problems? In fact, it was done in the beginning of the 20th century. Two British scientists, Ramsden and Pickering, discovered that solid particles can adsorb to the droplet layer. This droplet layer of particles is a mechanical barrier against coalescence. It makes system more stable. There are some advantages of using particles instead of surfactants. First is possibility of functionalization of these particles, for instance, of making them more biocompatible. Particles can be produced of different shapes, sizes, and different origins, including bio-origins. It's because fast development of material science in last decades. And what's the most important, particle stabilized emulsions are more stable than surfactant stabilized emulsions. It's because attachment to the droplet interface of particles is more stable. There are also some unique applications for particle stabilized emulsions rather than surfactant stabilized emulsions. For instance, capsule formation by sintering of particle layer. There are some roads of fabrication of stable Pickering emulsions like microfluidics, like mechanical steering, but today I'd like to propose our novel approach. It consists of two steps: ultrasonic homogenization and limited coalescence of droplets under the electric field. In our experiments, we used castor oil as continuous phase and silicon oil as disperse phase, and some types of particles: polystyrene, magnetite, polyethylene, silica particles. After vertical sonication, we obtain poorly stable emulsion, droplets coated by particles, but not completely. We need another step. This step is using electric field, because under the electric field there are dipolar interactions. They facilitate the process of coalescence, of merging of droplets. As we can see, when two droplets not completely coated by particles merge together, the total coverage of surface is increasing. Also, we can use increased DC electric field to induce some electrorotation to break agglomerates. Is also very useful for efficient formation of Pickering emulsions in our experiments. What is very important in our approach, droplet size increases under the electric field because after some events of coalescence, droplet size is bigger than in the beginning. And we can obtain such droplets. It's an example for polystyrene particles. We can see a very nice coverage by particles. Also, other types of material can be used to stabilize, like polyethylene and silica. As you can see, the process is very efficient. However, there are some limitations, again, some limitations, in this case with observing and monitoring process of formation by using only microscope and camera. It's not possible for larger volume of emulsion and for instance, magnetic particles because of non-transparency of this system. So natural candidate to monitor is using ultrasound. In our experiment, we use very simple ultrasonic system with two piezoelectric transducers, transmitter and receiver, and we were able to monitor the process of formation in line. We monitor the change of attenuation coefficient during application of electric field. One word about theory of ultrasound in emulsion. We probably know theoretical predictions from Epstein-Carr-Allegra-Hawley theory for particulates. This theory means that we should take into account intrinsic absorption of components and also other phenomena. In emulsion, there are thermal losses and scattering losses. These losses of energy depend on droplet size. In our experiment, we are in range of droplet sizes from 10 micrometers to 300 of micrometers. It means that during process of formation, we are on this monotonously increasing curve, increasing slope. So it's very important for our experiment. In general, we should include additional effect of particle shell in Pickering emulsion, but it's very challenging. So these predictions we made only for pure droplets without any particles. How about experiments? We obtain change of attenuation coefficient in function of time of application of electric field, and we could observe that after some time, the change of attenuation coefficient is limited. Also, it depends on concentration of silicon oil. We can see that this time of limitation of ultrasonic attenuation change is different for different concentration. Droplet size is limited. Also, change of attenuation coefficient is limited. What is interesting in our system, it's very simple relation between final droplet size after the whole process of electrocoalescence and number of particles used in the beginning to stabilize the system. For bigger droplet size, we need smaller number of particles. And we can see that also ultrasonic attenuation coefficient, a change of ultrasonic attenuation coefficient is sensitive to the droplet size. What's most exciting is that by using ultrasonic experiments, but using ultrasonic wave, we can establish some parameter like stabilization rate and say that, for instance, the fastest stabilization for this system is for these parameters. It's very nice because it's hard to say only by using optical observations. How about comparison between theory and practice? We can see some discrepancy, but this discrepancy is very important. It says that it's a need to develop some new theory or improve existing theories and include particle layer to this theory for Pickering emulsions when ultrasound is used to monitor the process of their formation. In our other experiments, we used magnetic Pickering emulsions, magnetic particles as stabilizers, for instance, for future applications in formation of capsules. So it's very important question if magnetic heating changes the emulsion structure. And after some preliminary results, we can see that there are no changes during process of heating because parameters, acoustic parameters in our experiments return to the primary values. It means that or there are no changes of structure during magnetic heating, or these structure changes are only temporary. To sum up, I hope that I showed ultrasound and DC electric field efficiently for Pickering emulsions, and ultrasound can be used also not only to formation, but only to monitor the process of formation, not only in the electric field, but also processes, dynamic processes in the magnetic field. In the future, we like to use ultrasound also to show efficient encapsulation during process of formation of capsules. It's very exciting in the future. I hope to show more results. And work was financed by National Science Center of Poland, and I thank you for your attention.